Hey SPI fans, Alex Hoskins here with you, and I'm the Director of Research and Development here at Storm Products. And today I'm really excited to talk with you about some brand new technology from the Roto Grip brand, the Transformer. Now the Transformer is the first ever HP 5-ball, and there is a ton of new technology on the inside that we're going to be looking at today. You see, I have a few visual aids on the table here, and we're going to go over some of the technicalities of this bowling ball, starting with the cover. This has the VR1 solid reactive cover. Now that's the same cover that was on the Gremlin, but it is the solid version and it is nano free. So this gives you a lot of versatility in the cover, and you're gonna see when we get to the weight block here, we're able to change the ball reaction of this quite a bit. So it's really good to have that VR1 cover stock on there that's going to allow you to get more left if you need, or use a little bit more surface in higher volumes of oil. But moving into the center, we have the Morph-Wing Core. And just like you hear in the name, wing, there are some wings on this. And these wings are what really differentiate this design from everything else that we've ever done. You can see they're very close to the shell of the bowling ball. And what they do is they enhance torque-induced precession. And we don't talk too much about torque-induced precession. We're more concerned as bowlers with torque-free precession, the actual flare of the bowling ball. But torque-induced precession is often missed, and it's really important for how your ball holds on to rotation and how it wants to go through the pins as it comes off the end of the pattern. So let's look at a deep dive of this, starting with the precession and how that's going to influence how this bowling ball comes off the end of the pattern. All right, so looking at the numbers of this Morph-Wing Core, we have 2.51 for the RG. Now for an asymmetrical ball, that's a little bit on the higher side. It's not a high RG ball by any means, but most of the ASIMs are in the 247, 248, 249 range. This one being a little higher at 2.51 means it's naturally going to get a little bit further down the lane, through the front of the lane a little bit cleaner. For total differential, we have 0.51. Now that's not really high on the total differential scale, but it is on the higher end. But the big reason for that is at 51 diff, we have plenty of room to go up post drilling if we take this morph wing out and we make that weight block much skinnier. We can get upwards of 60, even 65 total differential drilling through that. And if we leave it intact, we can actually reduce the total differential into the 40s if we want to. So you can really transform it to how you want to see it come off the end of the pattern. For the intermediate differential, we have 0.15. Now that's a sweet spot for us at Storm because it's asymmetric enough that we can put that PSA different distances away from our positive axis point and see some differences in ball motion, but it's not too much to where it's very sensitive when you drill it. Now, if you hit this Morph-Wing Core, you can bump that up to upwards of 30 intermediate if you need it for your particular game and what you're bowling on. So you can see this is very transformable core in order to get it to do what you want off the end of the pattern for your game in the environment that you're bowling on. Now, you might be asking, where is this morph wing on the surface of the bowling ball? And we have a diagram on the ball here for you. You'll see that I have a rectangular box on the bowling ball there, and the horizontal lines are at 4 and 5 inches away from the pin towards the PSA. And you can see that line's just drawn directly through the pin, down through the PSA. That Morph-Wing Core is 2.5 inches wide, so 1 1/4 on both sides. If your thumb or your finger holes end up hitting that spot on the ball, you're going to be going directly through that wing and really changing the dynamics of the bowling ball. I mentioned earlier about torque-induced precession, and precession's a big thing in bowling, but we really focus on one kind of precession, and there's actually 2 different kinds of precession. This Morph-Wing Core was designed to look at the opposite side of the precession that we don't really look at in the background of bowling balls, and that's torque-induced precession. So I'm going to give you guys a little crash course on precession here, and you'll see what I'm talking about of what makes this ball completely different than anything that we've done in the past. So what is precession? Precession is the change in orientation of the rotational axis of a rotating body. Now that's a mouthful. What does that mean? It means as something is rotating, there's an axis of rotation. If that axis moves, whether it moves on the surface of the ball or whether the ball itself moves, that is precession. Like I said, there's 2 different kinds of precession. The first one is torque-free precession. Torque-free is no external torque applied to the body. This is caused by varying moments of inertia. Now, when I say varying moments of inertia, all it means is that when I spin this ball or this bowling ball in different directions, it takes a different amount of energy to rotate the ball. Conveniently, we have a weight block inside the bowling ball. So if I spin it this way or I spin it this way, it's going to spin easier or resist spinning more in one or another of those orientations. So we have varying moments of inertia in a bowling ball. If we put our axis somewhere in between those varying moments of inertia, we'll see torque-free precession, and that is flare. We see those flare rings on our bowling ball. That is our axis migrating along the RG band that it started on. Now, the entire other side of precession that we don't look at as much is torque-induced precession, and this is pure gyroscopic precession. There is an external torque that is applied that is causing the precession. Now, that is exactly what these wings do on this Morph-Wing Core. When we're drilling into this, if we're missing this wing, you can see how close this wing is to the actual shell of the ball. And it's conveniently placed exactly where your ball migrates to, whether the ball is pin up or pin down, as long as you're using 4 to 5 3/4 inch pin to PAP distances, which are pretty standard in the game today. So those migrations are going to end up right at this, and that's actually going to cause a pull, a torque effect, to cause your ball to continue as it goes through the pins. So again, in bowling, there's almost no emphasis on the torque-induced precession, but on the torque-free precession, we're always looking at the flare of the bowling ball. So what I want to show you guys first is no precession. So you'll see I have a video here, and this video is going to be a ball on a float, and this float actually puts some air underneath the ball. And what it does is it behaves like a very low friction environment. So you'll see when I spin this, I have a little piece of tape on the positive axis point, and you can see that that piece of tape maintains the exact same place as it's spinning the entire time that it's spinning here. You can see the pin rotating around. That might be about 4 inches from that axis of rotation. So this is an example of an object that has the same moment of inertia around all 3 principal axes, and it doesn't have any static imbalance. So it will not change orientation. It will not precess. So that's the very basic side of it here. Now we're going to dive into torque-free precession. Now remember, this is what we look for as bowlers. This is the actual flare of the bowling ball. Now, to understand torque-free precession, I have a couple of other visual aids here, and these are very cool because these are actually scribed by hand, the RG bands of the bowling ball. So on the left here, I have a symmetrical bowling ball, and on the right, I have an asymmetrical bowling ball. So if you look at these, each of these bands represents 1/1000th difference in RG value. So when you hear this ball is 2.490, we're talking about the RG value of the X, the pin, the X axis. That's the lowest RG on the ball. If we go 1 band out, then we're at 2.491. If we go 5 bands out, we're at 2.495. So on until we get to the high RG axis, the Y. That's going to be the PSA. That would be the highest RG axis on the bowling ball. So in this example here, 2.542. This is going to be the highest that it gets, and we engrave the PSA on this. Now, as you get further away from that, the RG is getting slightly lower because you're getting closer to the pin, which is the lowest RG axis of the ball. And then on an asymmetrical ball, we do have the intermediate RG as well, and that falls somewhere in between, and it tells us how asymmetrical that the bowling ball is. Now I'm going to show you guys an example of torque-free precession. So again, we have a ball on the ball float here. We're going to start it spinning, and what you see is we go from that yellow colored marker on the axis to a red colored marker, and eventually we'll get to a green colored marker. So you can see that this ball is actually precessing across the surface of the ball, but the orientation of the ball is still facing directly towards us. You can see the axis is pointing straight at the camera there. So this torque-free precession occurs when there's varying moments of inertia across the ball, and it's rotated on an axis that's not one of the 3 principal axes, because we know that they're stable across those 3 axes. This could happen faster or slower depending on a few things. If your rev rate's higher, it's gonna happen a little bit faster. If you use a stronger layout, it'll happen a little bit faster. And if the ball has more total differential, it will happen a little bit faster as well. I just talked about rev rate a little bit. Here's the effect of rev rate on that torque-free precession. So 115 RPMs, we spun this ball here, and you can see we stay on yellow for a little while, and we get to green, and you can see how slow this is going across the surface of the ball here. Now, likewise, if we go 525 RPMs, and we set this to spin, you'll see that this happens significantly faster. Yellow, green, red. It happens much faster because that rev rate increased, okay? And you'll see something interesting about this is it actually gets all the way around the ball and keeps going in a circle. The ball is never done processing as it goes down the lane. We just run out of time because our ball hits the pins within a couple of seconds of us throwing it. But the big takeaway here is the faster your rev rate is, the faster torque-free precession happens. Now we're gonna roll some balls down the lane on a ramp. On the picture on the left here, we have the pin at 12 o'clock, so it's gonna be at 6 3/4, rotating around a very stable axis. We rotate this, or we roll this down the ramp, and you see we're directly on 20, and we stay on the 20 board the entire way down the lane. We don't see any push or pull, and as you would expect, there's no flare on this because we're rotating this around a stable axis. Now on the picture on the right, all we've done is we've put that pin at 3 3/8 inches away from the positive axis point. So we know that this is gonna have some free precession and it's gonna flare. Do we think this is gonna go straight, or is there gonna be some push or pull? Let's see what happens as we roll this ball directly down 20 once again. And you see, amazingly, it stays on 20 the entire way down the lane and behaves exactly like the ball on the left, regardless of all this flare on the bowling ball. And I think that's a common misconception. People look at flare and think that it directly affects the push or the pull or the rotation of the bowling ball, and it doesn't. Now that doesn't mean that it's not important, because it is exposing fresh new cover stock to the lane. And when we roll a bowling ball, we're not rolling it straight, we actually have some rotation to it. So the more fresh cover we expose to the lane, the more friction possibilities we're gonna have that's gonna make that ball line up in the direction of our rotation. So that was just kind of an overview of torque-free precession, and that's what we focus on as bowlers, the flare of the bowling ball. But we really wanna talk about what makes this design of this Morph-Wing Core unique, and that is torque-induced precession. It enhances torque-induced precession more than any design that we've ever done in the past. And we're gonna look at torque-induced precession right now. To understand it, we need to understand the center of mass. Okay, the center of mass is just a singular point in the ball where the mass in every direction relative to that point is equally distributed. So wherever that point is, every direction that you look, the mass is exactly the same. It's balanced. Now this is not to be confused with the geometric center of the ball. In my example on screen here, I'm gonna zoom in. This is a CAD image of that Morph-Wing Core. We'll zoom in, and we'll zoom in one more time here, and you can see that there's two different X's in this CAD program. One is the actual geometric center of the bowling ball, and the other is the center of mass. You can see they're very close together, but they're not quite in the same place. And if you actually draw a line directly through both of those X's to the surface of the bowling ball, you get the center of gravity. And you'll notice that the center of gravity always falls very close to where this Morph-Wing Core is. And that's gonna be a huge part of what helps keep this torque-induced precession as the ball goes down the lane. This inner weight block is 2.5 to 3 times heavier than this core material. So if we preserve some of that, we're keeping a lot more of that torque effect of that arm compared to when we're drilling it out. We can make the ball go significantly more forward. And you're gonna see how this affects rotation right now. So as we look at torque-induced precession, we have a left-handed and a right-handed example here. You're gonna notice a big difference when I start playing this. You'll see that we don't have multiple colored markers on the axis point anymore. You notice that there's only one. It's yellow. And that yellow axis is actually staying in the same place on the bowling ball, but the bowling ball itself is actually precessing. This is much harder to pick up with your eye and is a big reason why this is overlooked in the bowling industry. The right-handed example is exactly the opposite. That imbalance is on the other side of the ball. And you can see, once again, we don't see any precession across the surface of the ball. The entire ball itself is actually precessing and changing its rotation. How does rev rate affect this? We looked at it on torque-free. In torque-induced, we have 120 RPMs here, and I want you to watch how fast that pin spins around the bowling ball here. We let it go an entire 1.5 rotations, and it took around 10 seconds to go all the way around. Now remember, on torque-free, if we increased the rev rate, we saw a much faster rate of precession. This is a little bit counterintuitive. We double the rev rate here. Look at how much slower this torque-induced precession is going. Same entire 1.5 trips around the ball takes twice as long with double the rev rate. So this is great news for you guys with lower rev rates or lower ball speed, because this is going to be working even harder for you. Now, it doesn't mean that if your rev rate's really high or your speed is high, that it doesn't matter. It just has a little bit less effect on it. So as rev rate increases, that torque-induced precession has a little bit less effect on rotation. Again, we're going to roll some balls down the lane, and I want you to see the big difference on what happens with the rotation of the ball here. On the left, again, pin is at 12 o'clock here, so it's around a 6 3/4 inch pin, and you'll notice that that yellow axis actually stays in the same place, and the ball gains rotation as it goes down the lane. No flare at all because we're on one of the stable axes. Now, right-handed example here, again, pin at 12 o'clock. We just have the imbalance on the other side there. You can see that it's not migrating, it's not free precessing at all, but it is gaining rotation through torque-induced precession. Now, this is obviously an extreme example because we're not throwing the ball this slow, but your ball will hold on to a little bit more rotation and want to pull a little bit more to the left or to the right with this Morph-Wing Core because these wings are so close to the surface of the ball and they're extremely heavy. So just a quick summary. We started with no precession. Remember, that was when we rotated the ball that had no varying moments of inertia and no static imbalance. Stays in the same place the entire time. We then moved on to torque-free only. That was when the ball is precessing on the surface of the ball, but the ball itself is not actually rotating at all. So we see it go from the 3 different colored markers while it's facing directly towards the camera. We then moved on to torque-induced, which we spun it around a stable axis, so we don't see any free precession. But what do we see? We see the actual ball precessing gyroscopically there, and that has a huge influence on rotation. And then it gets really confusing because both of these things are happening when we throw a bowling ball down the lane. So you'll see we're actually getting those colored markers to change, and the bowling ball is precessing as well. So the combination of these two is really what makes this Morph-Wing Core and the Transformer really transform your game and transform how that ball comes off the end of the pattern to anything that you're going to be bowling on. All right, that was a technical deep dive on torque-induced precession and really looking into this Morph-Wing Core and the Transformer. What we want to do now is we want to put it to the test. We're going to have a very special two-handed guest where we're going to drill both above, below, and directly through that Morph-Wing to see how that ball comes off the end of the pattern for our two-handed players. And then I'm going to also throw the ball, more of a traditional one-handed player, and I'll drill one where my thumb hole hits that Morph-Wing Core, takes all that mass out, and I'll do another one where it's directly in the center of my grip and it's maintained throughout the drilling. So you're going to see some very different ball reaction off the end of the pattern and how much this ball goes through the pins with these different layouts from both one and two-handed players.